All right. So this is the third video of Weal Analysis Wednesday. And it's going to be that introductory material that I promised. Well, I didn't promise. I promised it to one guy in a comment, but I figured it would probably be pretty good of me to make this material so that if anyone was like confused about something, they could go to this video and get that explained to them. There's just some basic things that we need to know in order to succeed in real analysis and to understand these videos. If you're someone that already knows, like you have a math background, you've taken college level math, you're probably not going to need to know this, but if you don't have such a formal background, then this is probably a good watch for you. So this is the stuff you need to know for Weal Analysis Wednesday. You need to know what a set is. That's going to be pretty important. A set is an unordered collection of distinct objects. And we write sets like this. Curly bracket denotes a set. We write two curly brackets like this to denote that these things are in a set, and we separate elements by commas. Anything can be in a set. It's really free and loose. It doesn't really matter. So we could put like blue, Canada, 7, and axe. That's axe. And that's a set. It's a set of 4 elements. Blue, Canada, 7, and axe. There's nothing wrong with this set. It might not be the most useful set, but it is a set. It's an unordered collection of distinct objects. If X is an element of a set S, we write X in this little E thing, S. Read aloud as X is in S or X in S. So this is X in S. I could write something here. I could write blue is in this set because it's one of the elements. This is what set builder notation looks like. X such that, this is a colon. Also, you might see this written as X such that P of X. This vertical bar and this colon mean the same thing. They both mean such that. X such that P of X. This is called set builder notation, where Px is just any statement about X. So P of X could be X is even. So X such that X is even would look like, well, that means there is some integer such that 2 times the integer is that number. So this would be stuff like 2, 4, 6, also -2, -4, yada, yada, yada. There is a set that has nothing in it. It's called the empty set, and we write it with a circle with a slash through it, or curly brackets with no elements in it. I like the circle with the slash through it. Sometimes people write a phi like this, and it's like, really, dude? Or they write the phi like that, and I'm like, come on, just use verify. But, you know, that's neither here nor there. This little indenty looking thing, this C, that is containment. A is contained in B. That means everything in A is in B. Okay, this means if X is in A, then X is in B. A intersect B. This is what this little cap is read aloud as. This is everything that is in both A and B. Okay. Maybe I should clarify this. This is a statement that has a truth value. A is contained in B. This is a statement, whereas this is a set of elements. This is a set whose elements are everything in A and B. Similarly, A union B, this little cup right here is A union B. That is everything that is in at least one of A or B, or both. So if something is in A or B, then it is in A union B. A minus B, or take B, so it is kind of really interchangeable, is everything that's in A that's not in B. So maybe we draw our little Venn diagram here. We have A and B. A minus B would be just that. Because this stuff is in B, so we take it away. This is A minus B. Okay. A function, we write it like this, f from f colon A right arrow B. That means the function f goes from A to B. It assigns elements in A to elements in B. And it's a specific way of assigning those elements. A function is a mapping such that every element in A is mapped to exactly one element of B. So we might draw two little sets here. And we put some dots in them. 1, 2, 3, maybe a fourth one. A function is something such that maybe we assign this to this, and this to that, and that to this. This is a function because every input has exactly one output. And that is going to have some ramifications later. There's some other stuff we need to know. There are certain special sets that we like called fields. A field is a non-empty set. We denote it with this blackboard F right here, with two binary operations called addition and subtraction. No. Addition and multiplication. Denoted plus and this little dot. Fields have a few properties that we just, if something's a field, then these things are true. If A and B are elements of the field, then A plus B is equal to B plus A, and A times B is equal to B times A. This is commutativity. Well, there's another property, property number 2. If A, B, and C are all in the field, then A times the quantity B plus C is equal to A times B plus A times C. Yeah, maybe I put like parentheses around these, group these together. So if we have A times a sum, we can distribute the A. If A, B, and C are in the field, then associativity, if we just add three things together, it doesn't matter what order we do it in. There are certain elements of a field that are 0 and 1. That's what they're called. 0 is the additive identity. That means anything plus 0 is equal to itself. 1 is the multiplicative identity. That means anything times 1 is itself. Okay? And there's a fifth property of fields. Every element in a field has some additive inverse. Okay, that means A plus its additive inverse equals the additive identity. And also we have every non-zero element of the field has a multiplicative inverse, A inverse, such that A times A inverse is equal to 1, the multiplicative identity. This is true for, these two things are true for every element in the field and then every non-zero element in the field, respectively. Ordered fields have a sixth property. There's a non-empty subset, P, subset of F, called the positive elements, such that if A and B are positive, then A plus B is positive, and A times B is positive. And if A is non-zero, then A is either positive or negative A is positive, but not both. One really important thing about ordered fields is the triangle inequality. If x and y are elements of an ordered field, then the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y, where the absolute value of an element A, I'm actually curious, how does the book define absolute value? Is it the square root of a squared, or is it, they do it this piecewise way, okay. Where absolute value of A equals A if A is greater than or equal to 0, if A is in the positives, I guess, or the opposite of A if the opposite of A is positive. Positive. Well, I kind of ran out of space, but union 0. Union 0. Okay. Because the absolute value of 0 equals 0, which is, whoops, negative 0. We get a lot of mileage out of this inequality when we're working with the real numbers, and in metric spaces too. That'll come up later. In order to make the reals, we need one more property, which is completeness. Okay. An ordered field F is complete if for every set A of the field, A is a subset of the field, A is contained in the field, that is bounded above, that means there exists something in the field such that A is greater than or equal to, I just used A, B, for all B in A. There was something in the field that is bigger than or equal to everything in A. If every set that is bounded above has a least upper bound in F, then the field is complete. Why is this such a big deal? Well, let me give you a set here. The rational numbers are not complete. Take the set X in the rationals such that X squared is less than 2. This set has plenty of upper bounds in the rationals, but no least upper bound in the rationals. That's because, kind of, if you imagine, we have everything from negative root 2 to root 2, all these little, there's like a bunch of little holes between all the rationals. So any one of these is an upper bound, but there's always something in the set that's in between the upper bound and something in the set. And the way we make the reals is we add completeness. Say that so in the reals, what we call the supremum, which is the least upper bound of this set, exists in R. That's it. That's the axiom. Okay. Next, the Archimedean property. This is another really important thing about the reals. This is the way the book gives it. If a and b are real numbers with a greater than 0, then there is some n in the natural numbers such that n times a is greater than b. So we have two real numbers. 0, let's say like here's a and here's b. No matter how small a is, there is some n such that na is over here. And on the next page, maybe should have done this first, but I've organized kind of the most important sets that we're going to run into. Blackboard n, the way I draw this is I kind of make a line, then complete an n, but with it kind of starting below the top of this line, and I draw another parallel line until it meets this line, and that makes a blackboard n. These are the natural numbers. 1, 2, 3, 4, 5, etc. Start with 1, add 1, add 1, add 1, add 1, yada yada. And then we also have the integers, which is the naturals with 0 and the additive inverse of all these elements. So yada yada yada, negative 3, negative 2, negative 1, 0, 1, 2, 3. We have the rationals. Every number p divided by q such that p and q are integers and q is not 0. And then we have R, blackboard R, the reals, which are axiomatized by those 7 axioms we just gave. Can also be thought of as the completion of R. So Q, but then it's got a bunch of holes. We complete it by filling in all the holes and making a continuum, and that's the reals. That's really everything you need, except for, you know how we axiomatized, we have the completeness axiom. If A is bounded, or BDD to mean bounded above, then sup A is the least UB, that's upper bound of A. I kind of made up my own notation to deal with, like, instead of saying A is an upper bound of A, instead of having to say all of this, I made up a function, I guess. I write down A is in UB of A. What that means, I guess UB of A is a function from the set of all sets to the reals or something. UBA is all the upper bounds of A. That's how I that's how I use it. It's not standard. I don't see anyone else going around using this. I also similarly will sometimes write that if A is a lower bound of A. And I write UB and LB to mean upper bound and lower bound. I don't really see anyone else writing it like that, though. It's just to save me ink and writing time for my delicate wrists. So yeah, that's all you need to know for Weal Analysis Wednesday. I'm working on the third one. When I was in California for winter break, I had to work on unlined paper. So I'm transferring the proofs from the unlined paper to the lined paper. That's going to take some time, but it will be out eventually. I'll see it when it comes out.